Okay, I'm Bill Johnson,
Yeah, and I'm Eddie Pasmiño.
and we are the world-renowned authors of the colloid textbook. You can see right here, you can get your hands on this thing by Googling groundwater project and colloids, and this is everything we know about colloid transport and force media.
Yeah,
What
and
we wanted to do, oh, go ahead, Eddie.
yeah, and by the way, the book is open access, it's free. You can just download it and go through it. And is we hope that you get some interest in this topic.
And if you signed up for our email list, please tell us if you have, because we don't even know how to get a hold of this email list. If you want to talk to us, just send us our emails at our institutions, which you can get to by just Googling our names. Um, so we're interested in sharing this material with you, in helping any authors that want to use freeware to demonstrate concepts related to colloid transport. What we wanted to do today was to show you a module that we developed that mimics what's happening when you perform atomic force microscopy in colloidal probe mode, where you're bringing a colloid into proximity to a surface, approaching it and retracting it, and moving it around on the surface to assay interactions across the surface. So it's called force volume imaging. Eddie's got the Parti-Suite module open for this. It's called the AFM Force Volume Simulator. Eddie, why don't you say a few words about it?
Yeah, yeah. So the installer and I think we're gonna include this video as part of the how to use it. Also gonna be represented at Bill's website is William P. Johnson website research. And what we did is we use all the knowledge that was developed in Bill's group for I did more than a decade, almost 2 decades, and just build this simulator using DLBO theory, extended DLBO theory, and also some contact mechanics to try to mimic what an atomic force microscopy uh, is gonna measure in the real world. So that's the aim of this module.
Yeah, and this is a good point about the contact mechanics because you have deformation when the colloid comes into contact with the surface in this module. You do not have that in the XDLVO module, right? It treats the surfaces as non-deforming, right? They're non-contact. But in fact, in this module, you bring the colloid into contact, and so at any given separation distance is less than contact. So in the less than a couple nanometers range, depending on your steric interactions and things like that, you will start deforming the colloid, and you will get forces and energies that deviate from an XDLVO profile at those close distances. But that's actually very useful to know. And so though that deformation impact is useful to know, and you get that here.
Yeah, yeah. So I don't know. We can just show it. Um, what these do with the default parameters, which you can see here on the screen. By the way, like you can change anything here, but it's a good idea to have a sense of what they represent, right? So, for example, like if we can go through this, I can start just. We have a domain that represents what an actual sample that you can put in the AFM apparatus, and what we did here is just define 2D plane, and we have 20 locations per axis, so we have a uniform grid of locations. We're gonna evaluate the force volume in each of these locations. That's how it starts.
Okay, do you want me to mention?
Yeah.
So
No.
on the next thing is the colloidal probe, right? You've got a probe mounted on the cantilever that will approach and then retract from the surface, the domain. And so you can input the radius, you can input its density. I'm not sure if that has anything to do with anything, actually, the density of this colloid, but it's in there. Um, One thing we should mention that is we give source codes to people who get to know this stuff and want to run with it. And this one was derived from the transport source code. So it's got a bunch of parameters that are derived from the transport simulations. It's got a lot of extra code in it that doesn't apply exactly to the FM, but we didn't want to break anything by extracting code and realizing that any of you who code knows that it's hard to keep track of all the dependencies. And so we left a bunch of transport code in here, and I think that's why we have density in here.
Yeah.
Um, The density of the colloid actually is here nor there when it comes to AFM force volume imaging. So you have a grid mimicking how the colloid would be moved across the surface in probably a raster formation, going across a row, then down a column, and so on, so on and so forth. And so you've got all these parameters that you can change. Primary among them, though, for this exercise is the zeta potentials on the domain and on the probe, the colloidal probe. And the default parameters here is that those zeta potentials are negative. And of course, we know from excellent work done by other researchers, including Ellie Mellick's group, that this net negative zeta potential is not sensitive enough to pick up any nanoscale charge heterogeneity. And so if you want to create variability in the interactions so that they're not just monolithically repulsive, one needs to add some amount of surface coverage by nanoscale heterogeneity. And so that first box, the box underneath the cursor that Eddie is showing, is set to 0. There is no heterogeneity represented. And so maybe we should run this just to show what that looks like,
Yeah,
Eddie, and you
yeah,
can come in through the
yeah,
result.
yeah. I'm
Okay, why don't
going
you go
through
ahead?
that. Yeah. So when you set these are the default parameters, and as Bill mentioned, uh, it's representing the probe and the substrate as completely uniform in all the measurements that you can make there. So they have full repulsion between the two surfaces, and that's what the zeta potentials. So there you in actions in the action box you have the simulate force profiles. Just give it a hit, and what is going to happen is showing you is calculating 400 locations. There are 20 by 20 in each side, so make a 400 location grid, and it's going to generate the plots. And the first plot that we are seeing is the actual representation of this flat surface, and you can see in the x and y axis, it's an xy plane. You can see the dimensions, and you can see this domain has around like 2 micron plus minus 2, so it's like 5 micron per side. And this is the default orientation of this. This is a 3D plot, represents reality, you can say it. You have to wait a little bit more because after the locations are representing, now generating the other set of plots, what it's doing is calculating the XDLVO interactions for every one of those locations. And now we can talk more about the two plots. So I'm gonna maximize this first plot and we'll go ahead and just um, explain through it.
Well, so you can see the pattern here on the plane of the domain. Now, there's a y-axis here that represents the fraction of the zone of colloid surface interaction that's occupied by heterodomains, but we don't have charge heterogeneity, so all those values are 0, okay? But on the domain, you can see there is a circle that, well, actually, I can't see at this resolution, but I guess it's actually a diamond that
Yeah,
represents the location of the colloidal probe, the center point of the colloidal probe. But the circle is the zone of interaction between the colloid and the surface. And the radius of that is actually given in the text at the top of the figure. In this case, under the conditions that we input above, where we had a particular ionic strength and radius of colloid, the zone of interaction radius is about 90 nanometers. Okay, and that's what those gold circles represent. And so they are to scale on this representation of this assay domain. Okay, so that's what this plot is showing you. It gets more interesting when we add heterogeneity. But Eddie, why don't you say something about the profiles just so they understand what
yeah,
that's showing?
yeah. So as you can see, like as I also says here in the title, you can rotate this. So we're looking in a plan view, and the reason that this has a 3D component is because we want to show some other parameter that corresponds to each location, but because the surfaces are completely repulsive, they don't have any heterogeneity, this fraction of COI occupied by head domains is going to be 0 for all the points. And it's going to be populated with more elements in a bit when we look at the different scenarios. And as Bill mentioned, in every single point of these locations, we generate the very same profile. And this profile, if we can rotate this a little bit, we can see it from the side. You can see that like all the 400 profiles are exactly the same, and it's because the surface doesn't have any difference of aspect, especially it's the same surface everywhere, it's uniform. which is not a real good representation of real surfaces, but that's how the theory was developed initially. And you can see in the x-axis, the horizontal axis, you have the separation distance between the colloidal probe and the surface. And in the y-axis, you have the force that the probe is experiencing or is measuring at that location. And you can see it's almost zero when you're far away, and by far away I say like 200 nanometer. And when you go closer, you have a little bit of attraction, like force is negative, and then some repulsion, which is significant, that's created by the same sign of charges zeta potentials in the both surfaces. And then if you pass this barrier, you're gonna go to a primary minimum when basically the colloidal probe should stuck to the surface. And if you go and force it towards the surface, you have this hard repulsion that comes from Born repulsion in the DLBO theory.
Yeah.
Yeah, but the
And
main
you
point is everything is the same everywhere. Yeah,
and notice how there's an artifact here that makes it look like the series run horizontally. They don't. The series, it just happens with the data density that it looks like these are running in bars transverse to these profiles. But in fact, there are profiles for each location. It's just that they are identical, so they create this two-dimensional figure. And you'll see when we start to add heterogeneity that the profiles are associated with each location. Okay,
all right.
so why don't we go back to the input
Yes.
view and fiddle around with charge heterogeneity just on the domain.
Yeah. So what we're gonna do now is in the domain surface heterogeneity parameters, what we include in this model, which is part of the trajectory model, Trash-Happel, is that the surface can be represented as mean field, as we just saw, and we can have nanoscale discrete heterogeneity. And that we learn from experiments and modeling is you need to have an analysis of all these trajectories to find the heterogeneity for the colloid to attach. And in this way, we implement the same strategy to represent heterogeneity in this substrate that's going to be the sample for the AFM. So I think like zero point 0.2 will be okay, Bill. Something like
Yeah, do
20%.
20%.
Yeah. So
Yeah,
as soon as you have a value here and you input the value, it's going to show you the aspect of the heterogeneity in the surface. This is also a plan view, but this is focusing in a really tiny section of the substrate of the domain
yeah.
when you can have a single head domain, that's head mode 1. You can have head mode 5 when you have a large head domain surrounded by 4 smaller. Head mode 9, 1 surrounded by 8. And head mode 73 when you can have this different realization of the surface. And I'm gonna let you guys know, I'm gonna let Bill tell you why you have this kind of representations.
Yeah, I mean, and this actually comes from Eddie's thesis work, where if you want to understand for different sizes of colloids, what the surface looks like to explain multiple sizes of colloids attachment, well, then you're going to need what turns out to be a power law distribution of heterodomains, where you have very few of the largest ones and you have a geometric increase in the number of successively smaller heterodomains, right? And these patterns achieve that. So it's a useful model if you're trying to, these het modes other than one are useful if you're trying to explain attachment of multiple sizes. But that actually is more relevant in the transport model. So this one kind of shows what they look like, but it's actually most relevant in the transport model. For this mode, I would suggest just playing around with het mode 1,
All right.
having a single size heterodomain.
Yeah.
And so you got 20% fractional coverage.
Yeah.
You know, why we don't, so we have het modes 1, 5, 9, and 73. It's
Yeah.
really unfortunate we didn't end up with a 42, but that's something we can work on later.
Yeah.
Um, and I'm just kidding. So the heterodomain radius that's chosen by default is 200 nanometers. There's no specific reason. But if you look at papers, so Eddie started this work back in 2000, his first publications were in 2014. And then Cesar Ron, coming from the same institution as Eddie, continued this work, and he's got publications in 2020 that show that, these heterodomains should be sitting in the 100, sub 100 nanometer size range, okay?
Yeah.
And so 200 and lower are reasonable numbers to play with. And so depending on the colloid size. So this colloid size by default is actually a 1 micron colloid.
Yeah.
So it's not particularly large, not particularly small. And so just 200 nanometer heterodomains are big enough to fill the zone of interaction under most ion exchange conditions. And so this is just a default heterodomain radius. Many of you wonder, well, how do you even choose that? Well, it comes from running experiments of different colloid sizes, different fluid velocities, different ionic strengths to back out what that heterogeneity would look like. So if you want a scientific basis for choosing your heterodomain size, look at those papers by Cesar Ron, R-O-N, and Eddie Pazmiño. And again, you can look at those references in our textbook or book. It's not really a textbook, but
Yeah.
so there you have it. So Eddie, why don't you do some things?
Yeah, it's gonna run it, and just make sure that something to keep in mind. It runs fairly fast. Depends on the computer. This is a simulation of a static positions that change in the separation distance. But if you're gonna start with more or like more numerous head domains or like smaller head domains, it's gonna start to be slow. But it will run. It's gonna take some time. But it's gonna create the same plots, but now we're gonna see the influence of heterogeneity, which is pretty clear right now in this very first plot. We're gonna let the program finish the whole thing. Just explain to that. But notice that now in this figure one, now we have these vertical bars, and now the profiles have some variability. And we're gonna start with this one, Bill. I'm gonna go through it.
Yeah,
Yeah.
sounds good. Oh, you want me to talk?
Yeah.
Okay, so you can see AFRACT is given by, so AFRACT is the zone of interaction, the fraction of it that is occupied by the heterodomain. And of course, the heterodomain is a domain of charge opposite to the bulk surface. Okay, in this case, the domain that's being assayed. And so Eddie is rotating to show that the variability in AFRAC that you saw by those blue squares reaching different distances up towards unity, that's caused by the overlap of the zones of interaction, as shown in the gold rings, with the heterogeneity, as shown in the green circles. And so the more overlap there is, the more that the fractional coverage goes towards unity. Okay. So you can see this nicely in plan view, and that's what we encourage you to do. When you generate this three-dimensional plot, don't just look at the default angle, rotate it and get a sense of the relationship between AFRACT and this overlap.
Yeah.
And you want to talk about the
Yeah. Something
profiles?
to add here. Yeah. For example, just before going to that, you can actually use all these tools from the MATLAB plot to actually show you values if you want to look at those. And rotate this again, and you can see like the higher the bar is, the higher the overlap, or like as Bill said,
Yeah.
the green that is the head domain, the part of the surface that has an attractive electrostatic force, uh, is feeling the zone of influence of the colloid. And as you can see, like most of those are repulsive, but some of those are attractive, and you have all the in-betweens. And this reflects in the force profiles when some of the profiles still have that barrier, the repulsive barrier, but other profiles don't have any barrier. They go directly to favorable conditions. And you can see this clearly, how you have all this variability that's captured now by the simulator. And what we hope to do is with the real system, if you do this rastering, you're going to have all these distribution of forces, and we try to represent this from fundamental principles, that's the utility, one of the utilities of this module.
I think we're going to have a couch made with that shit. Um, so as you see, as Eddie said, the higher AFRACT is, the more favorable that interaction will be. And so as AFRACT increases, you lose the barrier, you dampen the barrier or eliminate it, and the primary minimum goes deeper. And so you have all those influences. You have a spatial variability to the surface by virtue of the heterodomains that exist on it. And one thing I should say, right? We admit that this is a house of cards that we've built by backing out these characteristics, using these simulations or representations, and comparing them to experimental data. But what's really interesting about this is that we know that colloids are stochastic. Not all of them attach, not all of them detach in response to perturbations. And a critical function that nanoscale heterogeneity provides that no other DLVO aspect provides is a stochastic outcome. Depending on whether the colloid trajectory overlaps the uh, heterodomain sufficiently to allow attachment is a stochastic process. And so this is the only element I know of that creates the stochastic impact. Now, one thing, Eddie, I want to mention that I forgot,
Yep.
we don't actually have it on our list of topics,
Yeah.
is if you go back to the input page, we've got roughness on there too. We can introduce
Yes.
nanoscale roughness.
Yeah.
And there's different roughness modes where you have a rough domain or a rough probe or both. Domains one, two, roughness models one, two, or three. I don't want to get too much into this, but the point I want to make is nanoscale roughness has an important impact on these colloid surface interactions because the scale of the interaction decreases with the radius of curvature of the surfaces. And so the roughness creates small radii of curvature that dampen the interactions. But the important point to make here is it dampens both attractive and repulsive interactions. Okay? So that you cannot, through roughness, flip the attraction from repulsive to attractive. You need charge heterogeneity to do that. Now, on the other hand, another aspect of roughness that is not taken into account here in the AFM simulator is or in the XDLVO, is the ability of roughness to create multiple points of contact, right? Once you create multiple points of contact, now you strengthen the adhesion. And so colloids do become less reversibly attached. They're harder to knock off once they're attached to a rough surface. But the roughness didn't flip the interaction from repulsive to attractive. What it did is strengthen the adhesion on whatever interaction occurred there. And so it's an important distinction between roughness and charge because a lot of people lump those together as heterogeneity, and indeed they are heterogeneity, but they have very distinct and critical impacts on these interactions, and it's good to keep those straight. So anyway, we have roughness in here, but it won't flip your repulsion to attraction. It will only dampen the interactions.
All right.
Okay, anything else?
Yeah, I think that's for this scenario, Bill. And now we're gonna go to the constructing and destructive interactions when you have heterogeneity also in
Great.
the colloidal probe. Yeah.
Yeah,
So in the next panel down below, we can add also this heterogeneity in the colloid. And because the colloid is fairly large, maybe like right now it's like 1 micron diameter, you can have like nanoscale heterogeneity distributed in the colloid. So if we make this value, for example, 20% as well, it's going to show you the same realization of the different modes of heterogeneity applied
yeah,
on the colloid. And
yeah.
we can use the
Now
same,
just keep it simple
yeah,
with head mode one.
yeah,
Yes. Yeah.
we still have headroom and we can have here the radius. And I would say something smaller makes sense here, like, I don't know, like 50
Yeah,
nanometer.
50 nanometer, that's a reasonable
Yeah,
number,
yeah,
right?
yeah. And
Okay,
now
50
it's ready to run,
nanometer.
basically, right? Yeah,
Yeah. I mean, we're guesstimating these sizes. That's all we can do at this point. Okay. So one thing we should say is while it's running is that the heterodomain on the colloid may overlap, sit over a heterodomain on the domain. And if they are sitting overlapping one another, they will repel one another because even though they're both, let's say, positively charged, that positively charged interaction is repulsive across that area of overlap. And Cesar-Ron set this up so that the model accounts for that, so that you have both constructive interactions, as we call them, where the heterodomain and the surface are oppositely charged, okay? Whether you're talking about the colloid or the domain, but they can also be like charged and add to repulsion. And so that's why this creates a different pattern than what we saw before. So Eddie, why don't you take it from there?
yeah. For example, you use these tools that come by default in the plot. For example, the data tips. You can just choose any of these locations. And for example, if we go to like a location that has no heterogeneity in the domain, still have a fractional area. The C value here is 0.3. It means 30% of that golden circle is going to be filled by some kind of hetero domain. But because we have,
Coming from the colloid.
yeah, yeah, exactly. It's not showing here in the domain, but it's going to be if the contribution is completely from the colloid heterogeneity. And for
Yeah.
example, if you go to like one that's fully in the green, it's not 100% because here is 68%, 0.68. It means that 32% is a destructive interaction from the colloid. So
Yeah.
now we have this all this variability, this introduced complexity when we have a heterogeneity in both surfaces. And this reflects right here in the COI and also in the profiles. I don't know, Bill, you want to add something else?
No, yeah, just so while we don't represent explicitly the heterogeneity on the colloid, it does manifest in these AFRACs.
Yeah,
And it's interesting to me that it produces a minimum. It looks like the minimum AFRAC is about zero point 0.3.
yeah,
I wasn't expecting. That's interesting.
yeah,
So, everywhere there is, everywhere across this domain, no matter where you are, you've got at least 30% of the ZOI filled by heterodomains. And so that's going to help with attraction. Now
yeah,
you have to flip the interaction from repulsive to attractive, you have to fill somewhere around 50%, right? That
yeah,
makes sense. And it varies a bit because of curvature of the colloid and other things, and the zeta potential and the ionic strength, but it's somewhere around 50%, or to be probably between 40 and 60.
yeah,
And and so that 30% group probably isn't enough to flip the interaction to attractive, but it certainly reduces the barrier.
yeah.
And so you can see it dampens the amplitude, as Eddie was just showing in the rotated profiles. Now there's less variability,
Hmm.
which is interesting, right?
Yeah.
So you can, I find it interesting to play with these scenarios in terms of what does heterogeneity on either phase do to the range of interactions that occur. And so that's
Yeah,
easily in this software.
yeah, and something to take in mind, I should add is um, this discrete heterogeneity uh, realization of the surface. Actually, when it's coupled with experiments with different colloid sizes, explain a lot of observations,
Yeah.
and we're confident that is a valid theory, is working in different scenarios, and is being refined by the time. Why not add it to this simulator just to have all these different representations of the surface that you cannot really see because they are so tiny, and the way that the colloidal probe is feeling in the colloidal scale with colloidal forces. And after doing this, which is purely mechanical in the sense that we are explicitly varying the location of the colloid and getting the forces, now the module go to the next step, which is actually generate heat maps. And I don't know, Bill, you want to explain about the what the heat maps are?
Well, let's just say some preliminaries about it. To generate a heat map, what you're doing is identifying if the profile shows a primary minimum and if it shows a barrier, right?
Yeah,
And then you want to display that spatially. So the program does its best to identify the zone in which one finds the primary minimum and the zone in the profile where one finds the barrier. And so it does that by default, but you have control over this. So if
yeah,
you look at the right side of the input window, if you don't think those values are quite right, if they're not really capturing the zones in which you find your features, you can adjust those. You can actually literally put the cursor in there and change that number.
yeah,
But let's just go with the default ones, because what it's saying here is the primary minimum is no further out from the surface than 5.7 nanometers, 5.68 nanometers. And that the barrier is no closer than 5.68, but no further than, oh,
500.
sorry,
Yeah,
5.68 nanometers,
yeah,
and no further than, well, of course, no further than 500 nanometers. It's giving you a lot of room.
yeah,
But the point is, you can change those limits. So based on these limits, you can let the model then represent this as a heat map. So go ahead and hit that, Eddie.
Mhm.
And this is, I think, helpful because it gives you a histogram and also the heat map. So Eddie, why don't you run through the histograms and the heat map?
Yeah, so very first figure, figure 3, we have a barrier map, which is showing in each location what is going to be the value of the force of the barrier. That's what it's saying here. And
Yeah.
the heat map showing you uh, the going from blue to red. When you go to values that are going to red, it means the barrier is higher, is more repulsive. The surface is more repulsive for the colloidal probe. And when you go to lower values, it means that in that section of the domain, you find lesser barrier or even go to repulsive. Yeah, I mean to attractive. That's what I mean. And in figure 4, you have the primary minimum, which if we see in plan view, you have this color code. It means how stable or how deep goes the primary minimum depending of the value here. And you can see the values going forces in the z-axis. We call this xy, right? This is the z-axis. And in the color you can have the bluish is going to be the deeper attraction, is going to be the more stable interaction between the probe and the domain when they are in contact. And of course, from these uh, heat maps, we can go to the and get the histograms. And I don't know if you want to add to that.
Yeah, I mean, it's just showing you then how the forces, which are all in newtons, by the way. So I noticed some of our figures don't have the units, but they're all in newtons. And so the primary and minimum there, you can see that there's a distribution that skews towards, the everything is in nanonewtons on this particular figure. That'll shift depending on your conditions, but in this one, it's, anywhere between 2 to 4 nanonewtons attraction, right? Negative values are attractive. So you can see that distribution among all of those locations, the 400 locations that were assayed. And then if you go to the barrier uh, uh,
This one right here.
distribution,
Yeah.
you can see it's bimodal. So you have the repulsive interactions, but they cluster around between 0 and, I'm going to say 0.75 times 10 to the minus 10th. So much weaker than what we just talked about. Right? These are thousandth of a nanonewton. So what do you call that? Um, I don't know. I probably should know, but I don't know. So, less than a thousandth of a nanonewton there. And then also this other cluster is more like 3,000ths of a nanonewton. So weak barriers, and that's consistent with the modulation of the barriers that we saw when we had heterogeneity on both the colloid
Right
and
here.
the.
Yeah.
So you can get the stats from all this. By the way, all of this is output in an Excel file for your.
Yes. Yeah.
So these images are really useful to kind of play with, but you can generate your own stuff based on this output. And I don't know, do you want to go
Yes.
through that real quick? Yeah.
Yeah. So when you finish doing all this simulation, you're gonna set an output directory. And for example, is getting into the default value. I can just put anywhere. I'm gonna select this folder and then I'm gonna save data to file. And what it's gonna create is gonna create Excel files will have all the location information, the profiles with force, and the barrier histograms and the primary minimum histograms. So all the information is in a tabular um, presentation that you can use for any analysis, for the analysis you want to do it. It takes a minute because it's saving to Excel has to internally create these Excel files, and they're fairly big to tell the truth. But it's good to have it. Yeah, so I think
That's good.
that's about it,
Yeah, and I want to
right?
say one thing I want to say about all this is, as I said before, we know we have a bit of a house of cards. We backed out these characteristics, right? But the model doesn't dictate what you put into it. You choose your heterodomain radii and all that stuff. So really the goal here is to represent what's relevant to colloidal transport, to colloidal interactions, what that heterogeneity might look like. You can imagine if you're trying to directly detect heterogeneity on surfaces using, for example, scanning electron microscopy with energy dispersive X-ray analysis, right? That's a very common technique. You will detect heterogeneity. You will. There's variation in signal on all surfaces that I've looked at anyway. The question is, what of that is relevant to colloids? And so we view this kind of freeware as guiding that investigation. You can look at this, and then you can start to look at what translates over to direct detection on surfaces using whatever assaying technique you might be using. Okay. I think the most direct, of course, is colloidal probe force volume imaging, right? You can make a direct comparison between these predictions and the results of that using this module. So it's meant as a guide towards understanding nanoscale heterogeneity on surfaces. We don't claim that we have this dialed in and accurate so much as we believe that we have a very useful construct that produces allows us to interpret colloidal transport behaviors, but also I think the next step is to try to directly assay heterogeneity on surfaces, independent means, spectroscopic or microscopic in terms of atomic force imaging and related methods, and reconcile
Yeah,
the theory and these measurements.
yeah, exactly. All right. So
Yeah.
I think it's just finishing up. Takes maybe 1 more minute, but all the data that we just showed to you and is gonna be there, so you can just use it for any further analysis. Right? Yeah, I
So
think.
if you have any questions for us as you're trying to use this and it's getting hung up, and by the way, when you download this and then try to run it, always right click and run as administrator. That's the easiest thing
Yeah.
to forget. If you forget that step, it's not going to work. None of these modules will work. You got to right click and run as administrator. If you have any questions for us, please email us. I'm at the University of Utah, william.johnson@utah.edu. Eddie, which is the email you want people to know about on your end?
I'm at EPM, so it's eddie.paspino@epn.edu.ec. We're in Quito, Ecuador, and we're happy to help. And yeah, so just to finish up, just gonna show you, just finish
Great.
saving the data, and you're gonna end up with a file that say like 001 output AFM. You can rerun more. It's gonna be 002, 003. You won't lose the data. And the very first spreadsheet is just the parameters, all the input file that we use to generate the data. The second one is the colloidal force for each location. Remember, we have 400 locations,
Yeah.
so we're going to have 400 columns, right?
Yeah.
And the first column is the separation distance. The same for all
Perfect.
the forces, van der Waals, EDL, acid base, steric. If we use it, we didn't use it for this example, but you can have that functionality. Born here, and we have the information for the histograms and the barrier and the locations and so on. So you can actually play with this and reconstruct the data and try to reconcile. If you are using AFM apparatus, it's going to be really interesting. We're going to be really interested to know what you can see and how you can fill that gap that goes from the heterogeneity to what the actual microscope is telling you in an image. All right,
Eddie, if you go back to the Born worksheet,
that's it.
assume those values were zero because, yes, that's
Oh yeah,
far away from the
yeah,
surface,
yeah.
right?
So
So it starts far away.
exactly, yeah. So bone repulsion at 500 nanometers is going to be zero, or insignificant. When you go really close to the surface, it starts to show up. And the closest we go is like 2 angstroms, zero point 0.2 nanometers, and that
Yeah.
is a really strong colloidal repulsion there, as you can see there.
Yeah.
Yeah,
Yeah.
and
Nobody would be able to
and you
sit
can
down
see
with
it's
it.
pretty much the same everywhere because Born is independent of surface charge heterogeneity, and
Yeah.
all these first principle from the LBO are built up in the model.
Yeah.
All right, cool. All right, so I think
All
that's
right.
it. Okay, so we're happy to collaborate or are open to any questions, as Bill said, and I think that's everything for today.
All right. Thanks,
Okay,
everybody.
okay, bye.
See you.